Most of you have probably heard about time travel, but how realistic is it? How can you calculate how fast or rather slow time passes for someone in comparison to others? This is all the stuff we're gonna cover in this video, and not only theoretically, but also like what we could do in real life and how big of effects moving and also gravity has on time dilation. So let's get started. You can either travel into the past or into the future, and probably a lot of you know which one is more realistic. It's the future travel, because when you travel into the past, you could theoretically kill your parents and they wouldn't be able to make you. But if you're not there, how could you have killed your parents? Which means your parents are alive, which means they made you, which means that you'll kill your parents. So this is one of the many paradoxes that happen when you think about past travel, really. So we're gonna talk about traveling into the future more. And traveling into the future, kind of at least, is what you always experience in your day-to-day life. Let's say there's somebody who doesn't move at all, he's just standing there. And then you, who's just traveling with a train, for say thousands of years. Because you're moving faster than he is, this means that your clock is ticking slower compared to his. For example, this is just an approximation, by the way. I can calculate, and we will calculate stuff like this a few minutes from now. And for example, if you traveled 1,000 years with your train and he just went standing still, your clocks would maybe be a few seconds apart in 1,000 years in the future. This is a really minimal effect. But the closer you get to light speed, this rises exponentially. Your time will just keep on getting slower. So let's start with the mathematics behind all of this. In February of 2024, the Parker Solar Probe came as close to the Sun as it never was. It was only distant about 6.3 million kilometers from the Sun, which is actually nothing compared to the diameter of the Sun, which is only 1.5 million kilometers itself. And I'm not gonna talk about the Parker Solar Probe all day long, but the velocity it had. It was about 430,000 miles per hour fast, which is enough. It could travel between the moon and the Earth in less than an hour if it were to constantly fly at this speed, which is about 92,000 meters per second. I will be using meters per second because they're the SE units and physics works in the SE units. Okay, and now let's use the formula. Delta T prime is equal to delta T times the square root of 1 minus v velocity squared divided by c squared, where c is the speed of light with exactly 299,792,458 meters per second, I think it was. And basically what this formula says, the delta T prime is how much, or rather how much slower, how should I explain this? For example, if we use this formula and out comes the solution 0.9, okay, 0.9. For a distant observer for who a year has passed, for the thing that's moving with the speed, only 0.9 years have passed. So basically the delta T square is how much time passes for itself compared to the other, okay? And now in the square root, it's 1 minus velocity squared divided by c squared. And so if you keep on increasing the velocity as it will get closer to light speed, this will keep the number we get as a solution will keep on getting smaller. And if you go faster than light, actually, this term phi squared divided by c squared becomes larger than 1. And 1 minus something larger than 1 is a negative number. And what is the negative number? What is the square root of a negative number? A complex number, which doesn't really make sense, because complex numbers are, well, complex and weird. So anyway, it went to, as I've already said, 192,000 meters per second. So now let's plug this velocity into the formula, and we get 0.999999795 unit. I guess you could use the unit delta t prime divided by delta t, but I'm not quite sure. Is there any mathematicians under you? If yes, then please tell me if this kind of makes sense at least. I don't know, I just thought it may work. So anyway, imagine if the Parker Solar Probe went at this velocity for 1 year. You know, this is only with the velocity, not the gravitational field around the sun. Our clocks and the clock of the Parker Solar Probe would be about 6.46 seconds off. Like a few seconds, that is like nothing for this enormous speed. Like, this is insane. So it is realistic that time travel, it's possible, very possible, but just not realistic on a larger scale, because a few seconds, like, no, that doesn't make a difference, like, not at all. Like, did you think it would be more time dilation or less? You can write it down in the comments if you want to. So, and now let's get to gravitationally induced time dilation. So first off, with the Parker Solar Probe as our example, do you think at this specific point, 6.3 million kilometers away from the sun, do you think the time dilation is stronger from gravity or from its speed? You can write it down in the comment if you want to. So, and basically the formula with which I calculated it is quite similar. It is delta t prime is equal to delta t times the square root of 1 minus 2gm divided by c squared r. So now, what is g? G is the gravitational constant, which has a value of about 6.67 times 10 to the negative 11. Okay? And for mass, m is of course mass. For m, we use 2 times 10 to the 30th, which is the mass of the sun, approximately. The actual mass of the sun is about 1.9 times 10 to the 30, but you know, it's simpler. And now if we put in these values, you know, r of course is the distance and c again light speed. If you put in these values, we get 0.99999764, which is slightly, and only very slightly smaller than the velocity induced time dilation, which has a value of about 0.999999795. Unit, you know, delta t prime divided by delta t, but that's just, you know, me, as I've already told you. So basically, both of the time dilations are off by about 0.000000031. So yeah, really they're both basically the same, but the gravitational induced time dilation is a little bit stronger. And you know, for if again the Parker Solar Probe were at that position 6.3 million kilometers away from the sun for a whole year, the clocks for a distant observer and the probe would be off by about 7.44 seconds, which is not a lot compared to 1 year. And if you like add up these two, also of course the Parker Solar Probe experienced both the gravitational time dilation and the velocity time dilation. It adds to about 14 seconds, which is like still infinitesimal. This is like basically no difference. But you know to whom it does make a difference? Satellites, because more specifically GPS satellites. Hey guys, while making this video, I just realized I really don't want to fit all of this into one part, because it would be like half an hour or something like that. So yeah, this is the end of part 1. I'll see you again in part 2, or rather you'll see me, because yeah, anyway, you get it, okay? So in the next part, I'll tell you more about, I'll actually be graphing the way these functions, or rather the time dilations, behave over changing r's, changing masses, changing velocities. You know, I've plotted functions for that, yes. But I'm not quite done editing, so I can't tell you exactly how many parts I'll do. But I think 2 will be enough. Hopefully. Maybe, yeah, I really can't say it. So yeah, thanks for watching the entirety of the video. If you liked it, you can like and subscribe. I would appreciate it a lot. So, thank you and bye.